The second big part of this chapter is algorithm on polygon, so we will discuss it now in the second video. What is a polygon? In the library, we represent a polygon by a list of points. So this is the code of Java, and this is a polygon with vertex 1, 2, 3, 4, 5, 6 vertices, and as you are seeing in the code, we add 0.11, 0.33, we add 0.91, point abscess 12, coordinate 4, 9, 4, and 1, 7, and finally, look at the code, we add again the point at the position 0. So we add again the first point we have added. Why do we do that? This is to loop back. So whenever we have a for loop that, for example, calculates the perimeter of a polygon, we want P of I plus 1, the distance between these 2 points, and the final point we will have to calculate the length of the edge by calculating the distance with the last point with the first point. So that's why instead of making a modulo or putting an if-else statement, we choose as a polygon representation to add the first point to loop back in the end of the list. And you know, in Java, whenever you add, you use the method add for lists, it will add in the order of arrival. So they will be added, the points in their order. So what is a polygon? A polygon is a plane figure bounded by a closed circuit composed of finite sequence of straight line segments. In its basic form, it is represented by ordered vertices given in clockwise direction or in counterclockwise direction. And in Java, usually the first vertex is also the last vertex, and we can click on this link to visualize an animation of polygon. This animation site is also provided by the authors of the book that is entitled Competitive Programming 3. That is our textbook for this course. Okay. I will draw a polygon. I will keep clicking until I am satisfied with the number of vertices, and then it displays no error. Okay. If I want to click and create another polygon, you can see that if I make a crossing polygon, it will display you must draw a simple polygon. This is a self-crossed polygon. There is 2 edges that cross, and for this type of polygon, the computation of the area of other things differ. So it is a more complex operation. So here in this chapter we deal with a simple polygon. Okay, we can continue using example polygons. For example, this is a concave polygon because if you draw a line, it will cross the edges of the polygon. This is an example of convex polygon. This is an example of mountain polygon, and this is an example of a maze. And they are all simple polygons. Perimeter, and you see it is the sum of the edge lengths. The edge lengths are the distances between each 2 consecutive vertices. Okay, so back to our lecture. This is the link to the polygon animation set of animations of the topics discussed in here. We continue our part 2, chapter 7, and we begin with the trivial perimeter calculation. As we have seen in the animation, it is the sum for a convex or concave with n vertices and that are given in clockwise or counterclockwise order. It is computed via this simple function which takes the polygon, and remember all our operation will have the first vertex doubled as the last vertex for that the for loop operates without a modulo calculation. So for I equals 0, I less than size minus 1, we know that if there is, for example, a triangle, the size will be 4 because we have doubled the first point, and we cumulate the result initialized initially to 0. We cumulate the distance between a vertex of index I p dot get I and vertex of index I plus 1. And this distance function we already saw in the previous chapter part. Of a polygon, there is a very effective and simple formula you can find, for example, here on Wikipedia, that calculates the area of a polygon by adding the areas of the consecutive triangles formed inside this polygon. And this is by computing the determinant. You put the matrix, 2 columns, with the abscess and ordinate of each point consecutively until point number n, and the area is the sum of the crossing xi yi plus 1 minus xi plus 1 yi. You keep crossing the matrix, and this area is sometimes positive and sometimes negative, whether the 3 points are in counterclockwise or in clockwise order. So this formula is not to demonstrate also here, but this is the implementation. You have area function that returns a double value. This double value, the area that I said it is either negative or positive, is returned as an absolute value. Okay, so it will be for a polygon, whether it is counterclockwise or counterclockwise order, it will always be returned as positive in this library. And you just get the point I plus 1, and you do the crossing and you cumulate in result. Another topic in the polygon is to check whether a polygon is convex or not. So I give you a list of points and you tell me whether this list of points is clockwise or counterclockwise. You have to tell me if this polygon is convex or not. What is the idea? What is a convex polygon? A convex polygon, just like in the left side of the figure from the textbook, is any line segment drawn inside the polygon does not intersect any edge of the polygon. So we took whatever 2 points we want inside the polygon. If we draw the line segment, this line segment must not cross any of the edges. If we find at least one line segment that crosses any of the polygon edges, this polygon, just like in the right part of this figure, is considered concave. So we are not, of course, going to draw each 2 point line segment and test whether it crosses all the edges or not. There is a very simple way to accomplish this. How we can do this to check whether a polygon is convex or not? We check whether all 3 consecutive vertices form a same turn. What does it mean form a same turn? So we check whether all 3 consecutive vertices form a left turn or all of 3 consecutive vertices form a right turn. How do I do that? I take, for example, point 0, point 1, point 2. I see to go from 0 to 1 to 2, I am going here counterclockwise. I take point 1, point 2, point 3. To go from 1 to 2 to 3, I am also going counterclockwise, so just like the previous set of 3 points. I take point 2, 3, and 4. Also, it is CCW. 3, 4, and back again to 0, it is CCW. So all the sets of 3 consecutive points taken form all the same turn. They form the turn here counterclockwise. If they all form the clockwise direction, it is also good. The thing that makes me decide the polygon is concave if I find a set of 3 points that does not behave like all the other sets. If I find at least one set of 3 points that, for example, turns right by opposition to the others that all turn left, or if I find some set of 3 consecutive points that turn right and some others that turn left, this means that the polygon is concave. How do I do that in code? This is the function. I say function because this is not an object-oriented programming. This is a function. It takes a polygon, a list of points, and it returns true or false whether this is a convex or not. How do I proceed? I take the polygon size, and if the size, first of all, is not 3, so this is not going to be a polygon at the first place. And if it is at least 3, so I get the first, second, and third point, and I check them to see if they are counterclockwise. I check 0, 1, and 2, and if they are counterclockwise, it will return true. If they are not counterclockwise, if they are clockwise, if they form a right turn, we say CW means right turn, also it will return the value false. No problem, but I want to remember this value, and the first one, returned value, must be equal to all the CCW answers for the next 3 consecutive points in turn. So I remember the first value, and I loop to see the triplets of points. Of course, here I am doing I plus 2, and this is why I have to check for the modulo. If I plus 2, if I am at the point before the last, I plus 2 does not exist, so I have to do the modulo. I go back to 1. Okay, and if I return one counter case example, I return directly false. I quit the for loop, and if I finish the for loop and never returned false, that means that all the directions are the same, whether they are all counterclockwise true or they are all counterclockwise false. So I return true, and this means that the given polygon is convex. This is a very useful and simple function that we will use later. Another interesting topic and problem is, given a polygon and a point, you want to know if this point is inside the polygon, like in the first 2 figures here, or outside the polygon. And also the solution comes when considering 2 consecutive vertices in the polygon by turn and within this given point. So we take the given point and we take that in turn every 2 consecutive vertices, and we check the angle P of I point P of I plus 1. This angle P of I, PT, P of I plus 1, we check it in turn, one angle after the other. If the sum of these angles is equal to 2 pi, we decide that the point is inside the polygon, else it is outside the polygon. Why do we do this? We do this because we know that the angle also has a sign. If the angle is for a given points that are counterclockwise, it will be positive, and if it is given in clockwise direction, the angle will be negative. So there is no problem to have negative angles, but the important thing is that the sum of the negative angles with the positive angles will be equal to 2 pi. If the sum is not equal to 2 pi, Like the third example, we have two positive angles and all the rest are negative, and if we sum all this, it will not be equal to 2 pi. Here we deduce that the point is outside the polygon. This is also a very beautiful problem solution, and here is the solution. We remember that we saw already in part 1 basics the CCW function, and we also saw the angle function. But the angle function we saw is returned in absolute value, so to know whether it is a positive or negative angle, we have to check if the points are in counterclockwise, so we consider it a summation. Otherwise, we deduce it, we consider the angle a negative angle, so we deduce it from the cumulative sum. And we return true or false whether this cumulative sum minus 2 pi is less than the epsilon. We always recall that we cannot see if this sum is equal to 2 pi because we are dealing with floating point. Instead of checking this, we check whether the difference is less than a certain epsilon, of course in absolute value. We talk in absolute value. So this is the n-polygon function, also ready to use inside the library given to you, and you now once explained, you will always remember it and you will use it whenever you need to. Another topic is cutting a polygon with a straight line. Two more topics to go. The one before the last is cutting a polygon with a straight line. This is a convex polygon, and this is the straight line in red, given by 2 points A and B, and we want to know the left side of the cutted polygon. So the input is the polygon, the big polygon Q, and a line defined by 2 points A and B. I want to make your attention here that so A is always or before B in X values, and we want as output the effect of this cutting will of course cut the convex polygon into two convex subpolygons, and the output will be one of these two, which one we will output the left side. So this is the problem here. Okay, we are giving this. How do we proceed? We will proceed by these three cases. So we take the polygon Q, that is input, and we visit the vertices Vi one by one. Okay, first point, second point, third point, until I go back to the first point again, and this is, I know that I visited all the vertices. And I take each of the vertices that I call Vi, and I see if A, B, and Vi are counterclockwise. So if A, B, and Vi are counterclockwise, this means that Vi is on the left side of the line and is part of the left subpolygon, so I have to add Vi to P. P is the left subpolygon I have to return. And then I check also whether it is on the left. I add it to P, but I check also the intersection of the line AB with the edge Vi plus 1. So I am walking along the edges also, not only the vertices. I see the edge Vi plus 1. For example, here I have an intersection. So if this intersection is not a null set, so if there is a point of intersection, in the schema you see it, this is the point C for the first time, and the point D the second time when its turns come. So I add also this intersection to P if it is not already a vertex. So suppose I vertex Vi, I added it, maybe this is the vertex Vi plus 1, just like the case of D, the intersection of A, B with the vertex D and the last vertex of the polygon is already a vertex. So if it is not already a vertex, I add it to the polygon P. And in case A, B, V, I are not counterclockwise, they will be clockwise. So it means VI is on the right side of the line. It will be part of the right convex subpolygon, and I will not add it to P, of course, because P is the left convex polygon. So this is the basic idea. Also, this is a very easy idea, and the implementation is easiest. I define line intersect segment function because I want to use it. I give a point A, B. This is the line. I give PQ. This is the edge. And I calculate here the line intersection segment. We could have used the R intersect function because the R intersect function takes also two lines, and if they intersect, it returns true, and it will give me the point of intersection. So we could have used this with a small modification in the code, but the authors prefer to put directly this function, and this will be used in order to calculate the cut polygon. So I continue the slides. This is the code for the function cut polygon. We know now it takes 2 points A and B that define a line, and it takes an input polygon Q, and we want as an output the left subpolygon cut by the line AB. And just like I told you here in the three cases, they are written in the code. You calculate the cross vector. Why? Because you want to know if they are counterclockwise or clockwise. Let's go back to the cross product slide to remember what does this cross product do. I clicked on the cross product from the part 1 of the chapter, and I remember here that the cross product is positive, then PQR is a left turn is 0, then PQR are collinear, and it is negative, then PQR form a right turn. So it takes two vectors, vector A and vector B, and it returns a value. We go back to our problem, and cross, we gave her two vectors, the vector AB and the vector A vertex I. Each time I give her vertex I, and I see if it returns. What will return? What will it return? Positive, 0, or negative. If positive, they form a left turn. If 0, they are collinear, A, B, and VI. And if negative, they are a right turn. Left 2, I keep it 0 for the moment, and if I is not the end, because I cannot get the end, okay, left 2 is the cross of vector AB and AVI plus 1. And now, first if is this point, if left 1 is greater than epsilon, is greater than, I want to see if it is positive, so I don't see if greater than 0 because I recall this is a floating point operation, so if it is greater than minus epsilon, then the line with the vertex, the line AB with the vertex are counterclockwise, and that's here I want to add VI to the polygon. So I say P, the polygon, the output polygon, which I created as a new array list of points that is empty first. I add to it the vertex I. P dot get Q dot P dot add what? Add the vertex I, which is Q dot get I. Okay, this is the first case. Second case, we will see if left 1 and left 2 are, if left 1, which is the cross product of AB and AVI, and the cross product of AB and A VI plus 1, if this cross product is negative. If this cross product is negative, it means what? It means one of this cross product is positive and the other is negative. What does this mean? It means that the line AB, one of the vertices VI and VI plus 1, one of them is on the left side and the other is on the right side of the line. And this means that they cross and that they intersect. In this case, I calculate the intersection, okay, and so this is the intersection calculation. The slide before it was defined this function, and I add it to P. Okay, I add it to P. And the third case, I do nothing, so I will not list it in this if. And to return P, I have, just like the convention we are working with since the beginning of this lesson, we want the polygon to be closed. So I will add the first point as also a last point, but I will add this only if the polygon is not empty. So if I have a left polygon at the first place, and if the size -1, the first, and if it is not already closed, okay, and if it's not already closed. Next and last topic is to find the convex hull of a set of points. You think this problem is difficult, but in fact it is the easiest problem of them all, and you will like it when I explain it. The convex hull set of point P considers these points in blue. What is their convex hull? It is the smallest convex polygon. We call it CH of P, where P are the set of points. What is CH of P? For which each point in P is either on the boundary of CH of P or in its interior. So it is the smallest convex polygon in which all these points are inside or on the border. Okay? How do I calculate? The problem here, I give you a set of points and you give me the polygon. Look to the schema to notice that the polygon is defined only by its vertices. So not all the points are the set of the polygon. Some of them are inside the polygon. This is a problem, okay? So you have to determine which points form the polygon and you have to give them in a counterclockwise order or clockwise order. So you have to give them in an order to form a convex polygon. Let's click on the visual animation. And to see the Grahamscan, you must draw at least 3 points. I must draw points. So let me draw the set of points. I want the convex hull for this polygon. I go, and the algorithm I will explain to you now. It is under animation. Look at the beautiful animation of this algorithm. You will understand it just in seconds. So this is the animation of the calculations. This is how the Graham algorithm proceeds in order to calculate the convex hull. Remember, we chose the points. They are applying the algorithm, and this is the final, this is finished. This is the final output. The convex hull that can contain all these points is the one denoted by the points in orange. Okay, let's go back and explain more. To find the convex hull of a set of points, just imagine that the points are nails, okay? That the points are nails that you can put in wood. And how to find the convex hull? Consider you have a rubber band that is long enough to be around all the nails, and you put it and you released it. And since this is a rubber band, it will enclose as small as possible. It will only be retained by the outer nails. So this is the convex hull. This is the convex hull. It is the rubber band in around the nails. And you can see that the rubber band cannot be concave, so it cannot enclose all the points with the details. It encloses them in a convex way. So finding the convex hull of a set of points has a natural applications in packing problems. If you want to pack a product, you want the box to contain the product, but you don't want the box to be wasting space around the product. Okay, so this is a common application in geometry problem, and most probably if you have a problem it will be about convex hull. So let's explain the easy algorithm to resolve this problem. Graham proposes an algorithm which is called Grahamscan algorithm of order O n log of n. Its solution is very simple, and once you understand it, you will say it's trivial. You take a pivot point between the set of points, you choose the pivot. The pivot is the bottommost, the lower point in the set, and between, if there are many lower points which have the same lower y, the minimum y, so you choose the rightmost one. Here we have only one lower point and we choose it as a pivot. In case you have two, you choose the rightmost one. This is first, you choose the pivot. And this pivot will be true in respect to all the other points. And then you do an angular sorting. This is the y-axis. Okay, this is the x-axis. Y equal 0, and you take the angles to all the points. This is an angle theta. This is from the point to the pivot with respect to y equal 1. This is the angle, and this is the third angle and the fourth angle. So you get the angles and you sort the points regarding with respect to the angles. So you will get, of course, the nearest to the angle 0 is the point 1, pivot is being the point 0, and then consider this is an arc that is opening. So in this direction the points are sorted from 1 to 2 to 3 to 4, 5, 6, 7, 8, 9, 10, 11 on the example. So you do an angular sorting with respect to the pivot, and this is very easy with the library. You will see in the next slide how easy it is. And after you have numbered, you have sorted the points, you consider a stack S of candidate points and the invariant in the stack. What does the stack hold? The stack, you know, last in, first out. The stack invariant is the following. The top 3 items in the stack must be what? They must be counterclockwise. So the top 3 elements, they must be like that. Okay, they have to be counterclockwise. They must do a left turn. If the top 3 elements are like that, this is a clockwise turn. This is a right turn. We don't want that. So we keep the top 3 items in the stack counterclockwise. How do we proceed? We initially insert 3 points. Which 3 points we initially insert? Let me erase the screen. Erase pen. First we add the last point of the polygon with the pivot with the first point in the sorting. So the last sorted point with the pivot with the first sorted point, and of course the angle is counterclockwise because the last one is bigger in angle from the first one, and the angle between the 3 points is of course a positive angle, and so they are, if we go 11, 0, 1, we are going counterclockwise. So this is the initial state of the stack. And we want that always the top 3 points in the stack. So here is our stack now, the initial state. We put 11, we put the pivot 0, and we put the element 1, and we check our condition. Of course it is true, the top 3 elements are counterclockwise. And then we proceed each vertex v in the sort. So we finished with 1. We will consider the point 2. If top 2 with v, so top 2, 0, 1 with the point 2. Let's see, 0, 1, 2. If they are going to be counterclockwise, so we have now 11, 0, 1, and we are considering the element, the point 2. We take 2, before we add it to the stack, we consider 0, 1, 2. Is 0, 1, 2 going to be counterclockwise? We push it to S. If it is not going to be counterclockwise, then we pop the last vertex added. We remove 1 and we reconsider the last 3 elements, the last 2 with 2. So we consider 11, 0, 2. But in this case, in fact, in this case, 0, 1, 2 are going to be counterclockwise. That's why I will keep 1 and I will add 2. So we continue with this example in C. We consider we have 11, 0, 1, and we are taking the element 2. We consider the element 2 here. Before we add the element 2, we check whether the last two elements with 2 will be counterclockwise. If they will be counterclockwise, I add 2. If not, I will have to remove 1 before repeating the check. So 0, 1, 2 will be counterclockwise, so I can add 2. And then I move to schema D. I added the element 2 and I consider now the element, the point 3. And I check 1, 2 with the point 3. Are they going to be counterclockwise? Look with me, 1, 2, 3. It is clockwise, it is not counterclockwise. So what does the code say, the algorithms of Graham say? If they are not going to be counterclockwise, then pop the last vertex added. What is the last vertex added? It is 2. So you have to pop 2 and you don't add anything, you repeat the test. You repeat, is 0, 1, 3 going to be clockwise? Yes, 0, 1, 3 is going to be clockwise. Then in this case, you add the element 3. Suppose 0, 1, 3, after removing 2 from the stack, was not going to be clockwise, you have to remove 1 also and then check again 11, 0, 3. So in this case, 0, 1, 3 was counterclockwise and we added 3, but again, when we arrived to 4, we discovered then 1, 3, 4 will be clockwise, and before adding 4, we were obliged to remove 3. And then we had 0, 1, 4. Is 0, 1, 4 going to be counterclockwise? Yes, so we add 4. We arrive to 5, and we have 1, 4, 1, 4 plus 5. 1, 4, 5 is counterclockwise, so we successfully add 5 to the stack. We arrive to 6, and we will see whether 4, 5, and 6, 4, 5, 6, look, this is an angle, this is a counterclockwise. We can use the cross product to tell us. And this is not going to be a counterclockwise, so we will have to remove the element 5 and check with 1, 4, 6. Is 1, 4, 6 going to be counterclockwise? Yes, so I add the element 6. And so on, we continue with 7, and then 8 and 9, they will be pushed and popped again from the stack because they will be forming clockwise angles, and then 10 and 11. And this is so easy. This is not the best programming practice to do a global variable, but I will leave it just like the writers define it. After that, after you finish the program, you can join all the functions in one file, just like I did. You can put the functions as static functions and not leave it instance functions. You can change the pivot parameter to make it a parameter, a variable inside the function, and not to make it a global variable. And you can do the settings you want. You can prepare your code. So the code is here. This is the function complex hull. It takes a list of points. It does not take polygons, so the last point in this list is not equal to the first. And that's why we see if the size is 3, so if it is a triangle, so the triangle is the convex hull of itself. All the triangles are convex. So all what we do is to add the first point as a last point and we return P, and this is the convex hull. This is a special case. In case it is not a triangle, we need to calculate the convex hull as described per the slides here. So what does Graham say? First, we want to find the index of the pivot. The index of the pivot is set first to 0, and then we iterate all the points in P, and to get the point with the lower y, and for equal y we want the point with the highest x. And if in the iteration we find it, we set p0 to it until we finish all the for loop, we finish all the points, so we have inside p0 the index of the pivot. What shall I do now? I create a temporary point and I switch the index of the pivot with the point at the index 0 with the point at the index of the pivot. So now I have inside P the pivot at the place 0. Okay, and then the variable, the global variable pivot, I have already defined outside the function. I told you I don't know why. I set it to get the point of at index 0. I already put at this index the pivot. Okay, now I have the pivot. I go to the sorting. How do I sort the elements inside P? I sort the points inside P using a comparator. So I call the function sort in the class collections and I give her the list P. The points, I don't want to sort them according to their natural order defined in compared to function in the beginning of the lesson. No, I don't want this compare to. I want to define a new compare method that is based on the angle. So I just simply um, I simply insert the comparator I want to use inside the sort mechanism. For those who are not familiar with this code technique, this is very easy. You just have to define an instance of a class that implements comparator of point because you want to compare a point with a point. In this class, you only have to define one function, one method. It is called public int compare and it takes two parameters which are of the same type parameter of the comparator interface, and you tell the function when to return 0, when to return something negative, and when to return something positive. Okay, and when it is according to the angle between um, point A between point A and point B and the pivot. Okay, so to decide whether point A is bigger than point B, we see the angle that is formed by A, the pivot, and the x-axis, and we compare it with the angle formed by B, the pivot, and the x-axis, and which angle is bigger, it will give me the bigger compare value. Okay, so I only define how to compare. I don't define how to sort. The sort function already exists in the library of collections. Okay, and now I have all the points inside P sorted, and of course the pivot will remain at the index 0 because it has the angle 0 because it is compared with himself. The angle pivot with x-axis, it is already the smallest. So once we do this, we move to the next step, which is to create the stack. We create an empty stack, and as promised, we put the last element in P inside first in the stack, then the pivot, and then the first element, the one after directly after the pivot. So I have n-1, 0, and 1 inside the pivot, and I continue from I equal to until n. Every time I check whether the last two elements in the stack, so whether s.get j minus 1 with s.get j, okay, we are keeping in j the size of the stack minus 1, and with I, p.get I, before we add p.get I to the stack, we see if they are counterclockwise. If they are counterclockwise, we add p.get I to the stack and we of course increment I. If they are not counterclockwise, we remove the last added element to the stack. So we remove the element of index s.size minus 1, and we don't add anything. It is until the next iteration to see if the top two elements of the stack with the current element we are dealing with are counterclockwise. Only when they are counterclockwise, we add this element to the stack. At the end of this loop, we have our convex hull inside S, and we simply return S, and this is the end of our chapter. Now I will go to the Java to the Java library, to the Java project, sorry, and if you can see, I copied all the redundant code into one Java file. For the competition, it must not be included in any package, but I left it in a package to differentiate it from the default package for now. For the competition, you must remove the first line, and you can see with me all the functions here. Look at the function names: convex hull, degree to radian, radian to degree, angle, area, counterclockwise, collinear, cross, cut polygon, distance, dot product, in polygon, is convex, line intersection, segment, normal, square. We have the perimeter function, two vector function, the epsilon, the pivot, the types point, the type vector. They are all defined here, and they are all used and explained during this lesson. What do you have more? You have in each file a run function. This is your homework. This is a very entertaining homework. Inside the run function, you have an example, a demo to show you all the functions that are used. For example, in circle, you have inside circle example, circumference example, diameter example. For the polygon, for example, we open the run function, and we can run this function to see a polygon in action and to see the cut of the polygon, what does it give us, and to see the convex hull of the polygon. And you know also that we have the Visual Go website, and you now took the geometry polygon, the convex hull, and you can try those animations to understand more the chapter. So I will leave you now. We will continue with next lectures with the problem solving.